Hello there, and welcome. Thank you for being here tonight. Whether you are lying in bed with the lights turned low or resting somewhere quiet with your eyes half closed, I am glad you found your way to this place. It has been a long day, I imagine. Perhaps a long week. And wherever you are right now, whatever weight you have been carrying, I want you to know that you can set it down. You do not need to do anything for the next little while. You do not need to think about tomorrow. You do not need to solve anything or remember anything or be anywhere other than exactly where you are. Just breathe and let the world outside grow a little smaller and a little softer and a little further away. Tonight, we are going to explore something extraordinary. We are going to talk about what happens when galaxies collide. Now, those words might sound violent. They might conjure images of cosmic destruction, of unimaginable catastrophe on the grandest scale nature can produce. And in a way, that is not wrong. When two galaxies meet, the forces involved are staggering beyond anything the human mind can truly grasp. Hundreds of billions of stars, trillions upon trillions of miles of space being reshaped. Gravitational fields so powerful they can bend the fabric of space-time itself. But here is the beautiful secret at the heart of tonight's journey. Galaxy collisions are not the violent crashes you might imagine. They are slow. They are graceful. They unfold across hundreds of millions of years, and in some cases, billions. Stars almost never actually touch one another because the distances between them are so impossibly vast that even as two galaxies pass directly through each other, the stars drift past like fireflies crossing paths in a wide, dark meadow. What sounds like a catastrophe is, in truth, more like a dance. A long, patient, beautiful dance that reshapes the universe itself. So tonight, we will trace that dance from its very first moment to its last. We will begin with the quietest force in the universe, gravity, reaching out across the void. We will watch galaxies spiral toward each other over timescales that make human civilization look like the blink of an eye. We will see stars being born in the chaos, tidal tales of light streaming across millions of light years, and supermassive black holes circling each other in a final embrace. And we will discover that the most destructive events in the cosmos are also among the most creative, the most beautiful, and the most peaceful. Some of these facts will surprise you. Some will fill you with quiet wonder. And some, I think, will change the way you think about change itself. Because galaxy collisions are not really stories about destruction. They are stories about transformation. About how the universe makes something new from something old. About how patience on a cosmic scale looks a lot like grace. If these calm explorations help you unwind, a gentle like or a quiet tap on subscribe would mean the world. It helps other restless minds find their way here too, one sleepy soul at a time. Now, let us begin. Let us start with gravity. Not the gravity you feel holding you to your bed right now, though it is the same force. Let us start with gravity at its most patient, its most delicate, its most impossibly gentle. Because before two galaxies can collide, something has to reach across the emptiness between them. And what reaches across that emptiness is gravity, the softest whisper in the universe. Gravity is the weakest of the four fundamental forces of nature. It is roughly 10 trillion times weaker than the electromagnetic force that holds atoms together. If you place two grains of sand side by side, the gravitational attraction between them is so faint that no instrument on Earth could detect it against the background noise of the room. You could spend your entire life sitting next to that second grain of sand and never feel the slightest tug. The force is there, technically, mathematically, but it is so close to zero that it might as well not exist at all. And yet gravity has a quality that none of the other forces possess. It never gives up. it never stops. It never fades to zero, no matter how far it has to travel. While the strong nuclear force operates only within the nucleus of an atom, and the weak nuclear force barely reaches beyond a single proton, and the electromagnetic force is easily shielded or canceled by opposite charges, gravity simply keeps going. It reaches across inches, across miles, across the spaces between planets and stars, across the voids between galaxies, across the entire observable universe. It gets weaker with distance, yes, following the inverse square law, dropping to 1/4 of its strength when the distance doubles. But it never disappears entirely. Even now, in this very moment, the gravity of a galaxy billions of light years from Earth is tugging on you. The force is so small that it would take more zeros after the decimal point than there are atoms in your body to write it down. But it is there. It is always there. Gravity is the force that never sleeps, never rests, never looks away. This is how galaxy collisions begin. Not with a bang, not with a flash, not with any event that could be called a beginning in any dramatic sense. They begin with a gravitational whisper so faint it barely exists. Two galaxies separated by millions of light years of empty space, each generating a gravitational field that extends outward in all directions forever. And somewhere in the void between them, those fields overlap. The pull is absurdly weak, immeasurably small, but it is real, and it is persistent, and it has something that no other force in this scenario has. Time. Billions of years of it. There is something remarkable about the patience of gravity at intergalactic scales. A gravitational signal between two galaxies separated by 2 million light years takes 2 million years just to cross the distance between them. That means the pull you would feel right now from the Andromeda Galaxy is based on where Andromeda was 2 million years ago, before modern humans had even evolved. Gravity works at the speed of light, which sounds fast in everyday terms, but across the distances between galaxies, it is achingly, beautifully slow. It is a conversation conducted in whispers that take millions of years to arrive. And yet those whispers accumulate. Over hundreds of millions of years, the faint gravitational tug between two galaxies begins to matter. Their random motions through space start to curve just slightly, just barely, bending toward each other like two leaves caught in a slow, invisible current. Neither galaxy decides to approach the other. Neither galaxy knows the other exists in any meaningful sense. But gravity knows. Gravity always knows. And given enough time, gravity always wins. The gravitational attraction between two galaxies depends on their masses and the distance between them, following Newton's law of universal gravitation, which, despite being over 3 centuries old, remains an excellent approximation at these scales. A galaxy like the Milky Way, with a total mass of roughly 1.5 trillion solar masses, including its dark matter halo, exerts a gravitational pull on everything in the universe. But the strength of that pull falls off with the square of the distance. At a separation of 2 million light years, the force between the Milky Way and Andromeda is extraordinarily small by any human standard. And yet it is enough. Over billions of years, that tiny force has been slowly, imperceptibly, drawing the two galaxies together. The universe itself has been working against this approach for most of cosmic history. The expansion of space, driven first by the momentum of the Big Bang and more recently accelerated by dark energy, has been pushing galaxies apart. Most galaxy pairs in the universe are indeed receding from each other, carried apart by this expansion, faster than gravity can pull them together. But the Milky Way and Andromeda are close enough and massive enough that their mutual gravity has overcome the expansion. They are gravitationally bound. They have been falling toward each other for longer than Earth has existed. and nothing in the laws of physics will prevent them from meeting. In our own cosmic neighborhood, this process is already well underway. The Milky Way and the Andromeda Galaxy are currently separated by approximately 2.537 million light-years. That is a distance so vast that light itself, the fastest thing in the universe, needs more than 2.5 million years to cross it. If you could somehow build a highway from here to Andromeda and drive at motorway speed without stopping, the journey would take more than 30 trillion years. 30 trillion. That number is so large that it ceases to have any intuitive meaning. It is simply a wall of time, too high to see over. And yet these two galaxies are falling toward each other at roughly 110 kilometers per second. That is about 250,000 miles per hour, a velocity that sounds extraordinary until you measure it against the distance still to be crossed. At their current speed, the Milky Way and Andromeda will not meet for another 4 to 5 billion years. The journey has been underway for far longer than that already. These two galaxies have been drifting toward each other since long before Earth existed, since long before our sun ignited, since a time when both galaxies were younger, smaller, and still assembling themselves from the raw material of the early universe. Consider for a moment what it means to fall towards something for billions of years. Human beings measure urgency in seconds. We feel the anxiety of minutes. We plan in days and weeks, and if we are thoughtful, in years or decades. But gravity plans in aeons. The approach of Andromeda toward the Milky Way is so slow that in an entire human lifetime, the distance between the two galaxies will shrink by a margin too small to detect with the naked eye. 100 generations of human civilization could rise and fall, and the two galaxies would appear to be in exactly the same position in the sky. The ancient astronomers of Mesopotamia, if they had possessed telescopes powerful enough to see Andromeda, would have measured essentially the same distance we measure today. And yet the galaxies are falling, constantly, inevitably, patiently falling. Every second, the gap closes by another 110 kilometers. Every minute, another 6,600 kilometers. Every year, another 3.5 billion kilometers. It adds up. Slowly, imperceptibly, it adds up. The gravitational dance between approaching galaxies is shaped not only by their visible masses, but by the dark matter halos that surround them. Every large galaxy sits at the center of an enormous cloud of dark matter, an invisible substance that accounts for roughly 85% of all the matter in the universe. We cannot see dark matter. We cannot touch it, taste it, or detect it with any instrument designed to measure light. But we know it is there because of its gravitational effects. Stars in the outer reaches of galaxies orbit faster than they should, based on the visible matter alone. Galaxy clusters hold together, despite not containing enough visible mass to bind them gravitationally. The cosmic microwave background, the afterglow of the Big Bang, carries subtle patterns that can only be explained by the presence of vast quantities of invisible matter shaping the early universe. Dark matter is everywhere, and it outweighs everything we can see by a factor of roughly 5 to 1. The Milky Way's dark matter halo is estimated to extend roughly 1 million light-years from its center, which means it reaches nearly halfway to Andromeda. That is 10 times the diameter of the visible galaxy. If you could somehow see dark matter, the Milky Way would not look like the thin, elegant disk of stars we picture when we imagine our galaxy. It would look like a vast, spherical cloud with a tiny, bright core, like a single, glowing ember floating inside an enormous, invisible balloon. Andromeda's halo is similarly vast. In 2015, observations from the Hubble Space Telescope's Cosmic Origins spectrograph revealed that Andromeda's gaseous halo, which traces the extent of its dark matter, stretches at least 2 million light-years from the galaxy's center in some directions. This means the halos of the Milky Way and Andromeda are almost certainly already touching, already overlapping, already mingling in the dark, even though the visible galaxies themselves are still separated by that vast gulf of apparently empty space. In a very real sense, the collision has already begun. Not between the stars, not between the bright spiral arms, but between the dark, invisible scaffolding that holds each galaxy together. Gravity is patient, but it does not waste time. While the stars are still millions of light years apart, the dark matter has already started to merge. The handshake has already happened. What remains is simply the long, slow process of the visible galaxies catching up to what the dark matter already knows. Before two galaxies collide, it helps to understand what a galaxy actually is. We use the word so casually, galaxy, as if it were a simple thing. A collection of stars, a bright smudge in a telescope. But a galaxy is so much more than that. It is an ecosystem of staggering complexity, held together by the most patient force in the universe, and everything about its shape, its size, its color, and its behavior tells a story about where it has been and where it is going. The Milky Way, our home galaxy, contains somewhere between 100 billion and 400 billion stars. That range might seem imprecise, and it is, because counting the stars in a galaxy you are inside of is a bit like trying to count every tree in a forest while standing in the middle of it. The exact number depends on how many faint red dwarf stars exist in the galaxy's outer reaches, and those small, dim stars are extraordinarily difficult to detect. Red dwarfs account for roughly 70% of all stars in the Milky Way by number, yet they are so faint that not a single one is visible to the naked eye from Earth. The nearest red dwarf, Proxima Centauri, is only 4.24 light-years away, and yet it requires a telescope to see. Imagine trying to count all the red dwarfs in a galaxy 100,000 light-years across, when you cannot see one that is just over 4 light-years from your front door. What we do know is that our galaxy is a barred spiral, meaning it has a central bar-shaped structure of older stars with 2 major spiral arms winding outward from the ends of that bar, along with several minor arms and spurs. The entire structure spans roughly 100,000 light-years from edge to edge, though recent studies using data from ESA's Gaia Space Observatory suggest the disk of stars and gas may extend even further, perhaps as far as 200,000 light-years when the faintest, outermost regions are included. That is a diameter so large that light, traveling at 300,000 kilometers per second, needs 100,000 years to cross from one side to the other. A signal sent from one edge of the Milky Way at the time the last ice age was ending on Earth would not yet have reached the opposite edge. But the stars are only the visible part. The Milky Way also contains enormous clouds of gas and dust, some of them hundreds of light years across, where new stars are still being born right now. These clouds are called molecular clouds or stellar nurseries, and they are scattered throughout the spiral arms like pockets of potential energy, waiting for the right trigger to begin collapsing under their own gravity and igniting new suns. The most famous of these is the Orion Nebula, visible to the naked eye as a fuzzy patch in the sword of the constellation Orion, a stellar nursery roughly 1,350 light-years from Earth, where hundreds of new stars are currently in the process of forming. The gas in these clouds is primarily molecular hydrogen, the simplest and most abundant molecule in the universe, and it is cold, just 10 to 20 degrees above absolute zero, cold enough that the molecules barely move, cold enough that the slightest nudge, the slightest compression can tip the balance from stability to collapse. The galaxy also contains the remnants of dead stars, white dwarfs, the dense, cooling cores of stars that have exhausted their nuclear fuel, slowly radiating away their residual heat over trillions of years. Neutron stars, the collapsed remains of more massive stars, spinning hundreds of times per second and broadcasting beams of radiation like cosmic lighthouses. And black holes of various sizes, from stellar mass objects a few times heavier than our sun, left behind when the most massive stars end their lives in supernova explosions, to the supermassive black hole at the galactic center, Sagittarius A star, which contains the mass of roughly 4 million suns compressed into a region smaller than the orbit of Mercury. And surrounding all of this, extending far beyond the visible disk, is the dark matter halo we spoke of a few moments ago. This vast, invisible structure contains 5 to 10 times more mass than all the stars, gas, dust, neutron stars, and black holes in the visible galaxy combined. The dark matter does not emit light, does not absorb light, does not interact with ordinary matter in any way except through gravity. But its gravitational influence is what holds the galaxy together. Without dark matter, the Milky Way's outer stars would be moving too fast for the visible matter to hold them in orbit. They would fly off into intergalactic space. The galaxy would simply come apart. Dark matter is the invisible architecture that makes everything else possible, the scaffolding upon which the entire luminous structure is built. Andromeda, formally designated Messier 31 or M31, is the Milky Way's nearest large galactic neighbor and the largest galaxy in our local group, the small cluster of more than 80 galaxies to which we belong. Andromeda is a spiral galaxy like ours, but larger. Current estimates suggest it contains roughly 1 trillion stars, perhaps 2 to 3 times as many as the Milky Way, spread across a disk approximately 220,000 light-years in diameter. It has its own central bar, its own sweeping spiral arms, its own population of molecular clouds and stellar nurseries, and its own supermassive black hole at its center, estimated at 100 to 230 million solar masses, making it somewhere between 25 and 60 times more massive than our own Sagittarius A star. What is remarkable about Andromeda is that you can see it with your naked eye. On a clear, dark night, far from city lights, Andromeda appears as a faint, fuzzy smudge of light in the constellation that bears its name. It is the most distant object visible to the unaided human eye. That smudge is the combined light of 1 trillion stars so far away that the photons entering your eyes have been traveling for 2.537 million years. You are seeing Andromeda not as it is now, but as it was when our ancestors, Homo habilis, were first beginning to shape simple stone tools on the plains of East Africa. Every time you look at Andromeda, you are looking back in time by more than 2 million years, and you are seeing the galaxy that will one day merge with our own. Andromeda has a rich system of satellite galaxies orbiting around it, much as the Milky Way does. The two most prominent are M32, a compact elliptical galaxy that appears to have been partially stripped of its outer stars by tidal interactions with Andromeda, and M110, a dwarf elliptical that shows signs of recent star formation despite being classified as an elliptical, which typically contain only old stars. These satellites are themselves participants in the gravitational dance, their orbits influenced by the larger galaxies around them, their fates tied to the eventual merger of the two great spirals they orbit. Not all galaxies are spirals, of course, and the shapes they take tell us a great deal about their histories, including whether they have collided before. Elliptical galaxies are smooth, featureless collections of older stars with very little gas and dust, ranging from nearly spherical to elongated like a rugby ball. They contain very little ongoing star formation because the gas needed to make new stars has largely been used up or expelled. Many astronomers believe that elliptical galaxies are the end product of galactic mergers, the calm, settled aftermath of collisions that scrambled the original spiral structures into something rounder and more uniform. The largest elliptical galaxies in the universe, the giant ellipticals found at the centers of galaxy clusters, are thought to have grown to their enormous sizes through the accumulated mergers of many smaller galaxies over billions of years. They are the ultimate merger products, the galaxies that have eaten the most neighbors. Irregular galaxies, on the other hand, have no defined shape at all. They are often chaotic, asymmetric, and full of vigorous star formation. Many irregulars are galaxies in the process of being disrupted by a nearby companion's gravity, their original structure pulled apart and rearranged by tidal forces. The Magellanic Clouds, the two small galaxies visible from the southern hemisphere that orbit the Milky Way, are classified as irregulars, and their distorted shapes are at least partly the result of gravitational interactions with our much larger galaxy and with each other. Then there are the peculiar galaxies, a category that includes some of the most visually stunning objects in the sky. These are galaxies caught in the act of collision, their arms stretched into long tidal tails, their cores connected by bridges of stars and gas, their shapes twisted into configurations that no single galaxy could produce on its own. Every peculiar galaxy is a snapshot of a collision frozen in time, a single frame from a movie that takes hundreds of millions of years to play. There is an atlas devoted entirely to these strange, beautiful objects. It was compiled by the astronomer Halton Arp and published in 1966 as the Atlas of Peculiar Galaxies. Arp cataloged 338 galaxies that did not fit neatly into the standard classification scheme devised by Edwin Hubble decades earlier. Many of them turned out to be galaxies in various stages of interaction and merger. At the time, the idea that galaxies could collide was still somewhat controversial. Some astronomers believed the peculiar shapes were intrinsic, that some galaxies were simply born strange. Arp's atlas, combined with the computer simulations that would follow in the 1970s, helped change that view. Today, it serves as a gallery of galactic encounters, a collection of portraits showing what happens when gravity brings two immense structures together across the void. Each entry in the atlas is a different moment in the story of collision, a different angle, a different mass ratio, a different stage of merger, frozen in light and catalogued for posterity. The distances between stars within a galaxy are so vast that this single fact transforms everything about what a galactic collision actually means. Our nearest stellar neighbor, Proxima Centauri, is roughly 4.24 light-years away. That is approximately 40 trillion kilometers, or about 25 trillion miles. If you shrank the sun down to the size of a grain of sand, about 1 millimeter across, Proxima Centauri would be another grain of sand roughly 6.4 kilometers away. Between those two grains of sand, there would be nothing. Just empty space and a few stray atoms of hydrogen drifting in the dark. No other stars, no other planets, nothing visible at all. Just a 6.4 kilometer void with a sand grain at each end. Now multiply that emptiness by hundreds of billions. A galaxy like the Milky Way contains perhaps 200 billion stars, but it is overwhelmingly made of nothing. The average distance between stars in our region of the galaxy is about 4 to 5 light years, meaning there is a vast, lonely gulf surrounding every single star. If you could fly through the Milky Way in a spaceship, what you would experience is not a crowded city of stars, but an enormous, echoing emptiness with tiny points of light scattered unimaginably far apart. You could fly for years at the speed of light and pass nothing at all. The galaxy is, to a remarkable degree, empty space with a few specks of matter floating in it. This is why, when two galaxies collide, the stars almost never hit each other. The chance of any two individual stars colliding during a galactic merger has been calculated by astronomers and is essentially zero. Not small, not unlikely, essentially zero. The analogy that is often used is two swarms of bees passing through each other in an open field. The bees are so small and the gaps between them so large that they would sail past one another without a single collision. But even that analogy dramatically understates the emptiness. Stars are incomprehensibly tiny compared to the spaces between them. If you represented every star in the Milky Way as a tennis ball, you would need to spread those tennis balls across a volume larger than the entire solar system to maintain the correct proportions. Two galaxies passing through each other is like two such collections of tennis balls, each spread across solar system-sized volumes, drifting through one another. Not a single tennis ball would come within millions of kilometers of another. What does collide, however, is the gas. Unlike stars, which are compact objects separated by light years of empty space, the gas clouds within galaxies are vast, diffuse structures, some of them stretching across hundreds of light years. These molecular clouds are sparse by any terrestrial standard, containing perhaps a few hundred to a few thousand molecules per cubic centimeter, compared to the roughly 25 billion trillion molecules in every cubic centimeter of the air you are breathing right now. But they are enormous, and when two galaxies merge, these enormous clouds cannot pass through each other the way the stars can. They collide, they compress, they heat, they fragment, and from that compression, entirely new generations of stars are born. When two gas clouds moving at different velocities collide, the kinetic energy of their motion is converted into thermal energy, heating the gas at the point of impact. But the heated gas also radiates that energy away, and as it cools, it becomes denser and more unstable. Regions within the compressed gas begin to collapse under their own gravity, pulling in more and more material until they reach the temperatures and pressures necessary to ignite nuclear fusion. A new star is born, and in a galactic merger, this process does not happen once or twice. It happens millions of times, across millions of light years, in a cascading wave of stellar creation that can persist for tens of millions of years. This distinction between stars and gas is one of the most beautiful aspects of galactic collisions. It means that the merger is simultaneously gentle and violent, peaceful and creative, all at once. The old stars drift serenely through the encounter, barely noticing that anything has changed. Meanwhile, between them, the gas is being compressed into the densest, most fertile conditions the universe can produce, and entirely new generations of stars are being born from the turbulence. A galactic collision is, paradoxically, both the quietest and the loudest event in the cosmos, depending on which component you are watching. Gravity does something extraordinary to galaxies as they approach each other. Long before the main bodies of the galaxies overlap, long before the gas clouds collide or the stars begin to intermingle, gravity reaches out and begins to reshape each galaxy from a distance. This reshaping is caused by tidal forces, the same kind of forces that cause ocean tides on Earth, but operating at a scale that can distort objects spanning 100,000 light years. Tidal forces arise because gravity is not uniform across a large object. The side of a galaxy facing its approaching companion feels a slightly stronger gravitational pull than the side facing away, because it is slightly closer. This difference in pull, the tidal force, stretches the galaxy along the axis connecting the two objects, squeezing it along the perpendicular axis. On Earth, the moon's tidal force stretches the oceans by perhaps a meter or two, creating the familiar rise and fall of the tides. In a galactic encounter, the tidal force can stretch an entire spiral arm by tens of thousands of light years, pulling stars and gas out of the galaxy like taffy being drawn by invisible hands. The physics of tidal forces is elegantly simple. The tidal force depends not on the distance to the perturbing object, but on how rapidly the gravitational field changes across the extent of the body being stretched. A nearby, less massive object can produce stronger tidal forces than a distant, more massive one, because the gravitational gradient is steeper. This is why the moon, despite being far less massive than the sun, produces larger tides on Earth than the sun does. The moon is closer, so the difference in its gravitational pull between the near side and far side of Earth is proportionally greater. In a galactic encounter, as two galaxies approach each other, the tidal forces grow rapidly, increasing as the cube of the decreasing distance. This means that even a modest reduction in separation can produce a dramatic increase in tidal distortion. A galaxy that appeared perfectly undisturbed at a separation of 10 million light-years can be visibly warped and stretched at a separation of 1 million light-years. The result is one of the most visually spectacular phenomena in all of astronomy: tidal tails. As two galaxies approach and begin to interact, the tidal forces pull long streams of stars, gas, and dust out of each galaxy, stretching them into enormous luminous ribbons that arc across hundreds of thousands of light-years of space. These tidal tails are not explosions or ejections. They are gentle extractions, pulled slowly from the outer edges of each galaxy by the differential tug of the other galaxy's gravity. The process takes tens of millions of years, and the resulting structures can be staggeringly beautiful, sweeping curves of starlight drawn across the darkness like the brushstrokes of a cosmic artist. The formation of tidal tails was first explained mathematically by brothers Alar and Juri Toumre in their landmark 1972 paper, one of the most influential studies in the history of galactic astronomy. Using computer simulations that were remarkably simple by modern standards, modeling each galaxy as a collection of just a few hundred test particles orbiting a central mass, the Toumres showed that tidal interactions between two disk galaxies naturally produce long, curving tails of material. Their simulations reproduced the shapes of known interacting galaxies with striking accuracy, demonstrating that the peculiar shapes Holt and Arp had cataloged were not deformities, but the mathematically predictable consequences of gravitational interaction. The universe was sculpting galaxies through collision, and the Toumres had discovered the chisel marks. The Toumres also made a prediction that would prove enormously influential. They proposed that galactic mergers could transform spiral galaxies into elliptical galaxies, that the disordered, scrambled stellar orbits produced by a violent merger would settle over time into the smooth, featureless, pressure-supported structure characteristic of ellipticals. This idea, known as the Toumre merger hypothesis, was controversial at the time but has since been confirmed by decades of increasingly sophisticated simulations and observations. Many, perhaps most, of the elliptical galaxies in the universe were once spirals that were transformed by merger. The antennae galaxies, also known as NGC 4038 and NGC 4039, provide perhaps the most famous example of tidal tails in the observable universe. These two spiral galaxies, located roughly 45 million light-years from Earth in the constellation Corvus, are in the midst of an ongoing collision that began a few hundred million years ago. Their two tidal tails extend outward from the merging cores like the antennae of an insect, which is how they got their name. Each tail stretches across roughly 500,000 light-years of space, which means the total span of the antennae system, from the tip of one tail to the tip of the other, is more than 5 times the diameter of the Milky Way. These tails are not thin wisps. They contain billions of stars, vast clouds of hydrogen gas, and active regions of star formation. Hubble Space Telescope observations of the antennae galaxies have revealed thousands of young, bright star clusters in the overlap region between the two galaxies, clusters that did not exist before the collision began, and that owe their existence entirely to the compression of gas triggered by the merger. The youngest of these clusters are less than 10 million years old, mere infants by cosmic standards, born from gas that was squeezed to the breaking point by the forces of the collision. In the antennae, we are witnessing creation in real time, new stars forming by the millions in the chaos of a cosmic encounter. The mice galaxies offer another beautiful example. Formerly cataloged as NGC 4676, these are two spiral galaxies in the constellation Coma Berenices, about 290 million light-years from Earth, that are in the early stages of a merger. Each galaxy has developed a single long tidal tail, and together they look remarkably like two mice running side by side with their tails streaming behind them. The tails of the mice galaxies have been studied extensively with the Hubble Space Telescope and contain numerous star-forming regions, knots of gas that have been compressed by the interaction and are collapsing to form new stellar clusters. In these tidal streams, stars are being born not within a galaxy but between galaxies, in the long filaments of matter strung across the void. Stars born in exile, formed in the debris of an encounter, belonging to no galaxy at all until gravity eventually pulls them back into the merged remnant. Sometimes tidal forces do something even more remarkable than creating tails. They create entirely new galaxies. Tidal dwarf galaxies are small, gravitationally bound collections of stars and gas that form within tidal tails themselves. As material is pulled out of a galaxy and strung into a long filament, dense regions within that filament can begin to collapse under their own gravity, accumulating enough mass to become self-sustaining. These tidal dwarfs are genuinely new galaxies, born not from the primordial gas of the early universe, but from the recycled material of existing galaxies, pulled free by the forces of a collision. They are among the youngest galaxies in the universe, and their very existence is proof that galactic collisions are not merely destructive. They are creative. They build new things from the fragments of the old. Tidal dwarf galaxies have been identified in numerous interacting systems. The antennae galaxies, the mice galaxies, and the NGC 5291 system all show evidence of tidal dwarfs forming within their tidal debris. These small galaxies are typically a few percent the mass of the parent galaxies and contain primarily young blue stars and recycled gas enriched with heavy elements from the parent galaxies. They are distinct from other dwarf galaxies in the universe, which are typically dominated by dark matter. Tidal dwarfs, being formed from the outer edges of disk galaxies rather than from primordial material, are expected to contain little or no dark matter, because the dark matter in the parent galaxies is distributed in a diffuse halo that is not concentrated enough to be pulled into tidal tails. This makes tidal dwarf galaxies natural laboratories for studying the behavior of galaxies without dark matter, a rare and scientifically valuable configuration. There is a particular type of galactic collision that produces one of the most striking structures in all of astronomy. When a smaller galaxy plunges directly through the center of a larger disk galaxy, almost like a bullet passing through a target, the gravitational disturbance propagates outward through the larger galaxy's disk, like a ripple spreading across a pond. This expanding wave compresses the gas and dust in the disk as it passes, triggering a ring of intense star formation that moves outward from the point of impact. The result is called a ring galaxy, and it looks exactly like what it sounds like, a bright ring of young, hot, blue stars surrounding a relatively empty center, as if someone had thrown a stone into a cosmic pond and frozen the resulting ripple in starlight. The most famous ring galaxy is the Cartwheel Galaxy, located roughly 500 million light-years from Earth in the constellation Sculptor. Roughly 200 to 300 million years ago, a smaller companion galaxy passed directly through the cartwheel's disk. The gravitational shock wave from that passage is still propagating outward, and the ring of star formation it triggered is enormous, spanning roughly 150,000 light-years in diameter, making it larger than the Milky Way itself. The ring is expanding outward at roughly 200,000 miles per hour, sweeping up gas and compressing it into new stars as it goes. The Cartwheel Galaxy was one of the first targets observed by the James Webb Space Telescope after it began science operations in 2022. And the infrared images revealed extraordinary detail in the ring structure, including individual star-forming regions, radial spokes of gas and dust connecting the outer ring to a bright inner ring near the galaxy's core, and a complex inner ring that suggests the collision triggered multiple waves of expansion, like two ripples from the same stone, propagating outward at different speeds. The JWST images also revealed that the spokes connecting the inner and outer rings contain dust-rich regions where stars are actively forming, suggesting that the galaxy's reconstruction is not limited to the ring itself, but extends throughout the structure. What makes ring galaxies so remarkable is their geometric perfection. In a universe of irregular collisions, partial mergers, and chaotic tidal interactions, a ring galaxy requires an almost impossibly precise alignment. The impacting galaxy must pass through the center of the disk, not off to one side, and the angle of approach must be close to perpendicular to the plane of the disk. If the geometry is even slightly off, you get a distorted ring or an asymmetric structure or no ring at all. The Cartwheel Galaxy exists because hundreds of millions of years ago, a small galaxy happened to approach a larger one at exactly the right angle, at exactly the right position, at exactly the right velocity. The beauty of the ring is a record of that precision, a geometric memory of a perfect collision preserved in starlight. The Hoag's object is another ring galaxy, though its origin is less certain. Located roughly 600 million light-years from Earth, it consists of a nearly perfect ring of young, blue stars surrounding a much older yellow core with a dark gap between them. The ring and the core appear almost completely disconnected, as if someone had drawn two concentric circles in the sky with nothing connecting them. The origin of Hoag's object has been debated for decades. Some astronomers believe it is the result of a collision similar to the one that produced the Cartwheel, while others suggest it may have formed through a different mechanism, perhaps involving a bar instability that redistributed the galaxy's mass into a ring configuration. Whatever its origin, Hoag's object is one of the most geometrically perfect objects in the sky, a ring of starlight so clean and circular that it looks almost artificial, as if it were designed rather than born from the chaos of cosmic interaction. When galaxies approach each other closely enough, something dramatic happens to the gas within them. As we touched on earlier, gas, unlike stars, cannot pass through other gas without consequence. As the gas clouds of two merging galaxies begin to overlap, they collide at velocities that can exceed several hundred kilometers per second. The impact compresses the gas to extraordinary densities, heating it to millions of degrees in some regions, while simultaneously creating pockets of cold, dense material in others. These cold, dense pockets are the seeds of new stars. And when galactic gas collides, it does not produce a handful of new stars. It produces millions. This phenomenon is called a starburst, and it is one of the most spectacular consequences of a galactic merger. During a starburst event, a galaxy can produce new stars at a rate 10, 50, or even 100 times greater than its normal rate. The Milky Way currently forms roughly 1 to 3 new stars per year, a modest, steady pace of creation that has continued for billions of years. But during the peak of a major merger, the combined system can produce hundreds of new stars per year, and in the most extreme cases, thousands. The night sky of a planet inside a starburst galaxy would be blazing with young, hot, blue stars in every direction, clusters of newborn suns lighting up the gas around them in brilliant shades of pink and violet, a sky so bright and crowded that true darkness might never fully fall. Starburst galaxies are among the most luminous objects in the universe. The young, massive stars they produce burn through their hydrogen fuel rapidly and shine with extraordinary intensity, particularly in ultraviolet and infrared wavelengths. A single star 50 times the mass of the Sun can produce 1,000,000 times more light than our Sun, despite having only 50 times as much fuel to burn. These luminous giant stars live fast and die young, exhausting their nuclear fuel in just a few million years compared to the 10 billion years our more modest Sun will endure. Their brilliance is temporary, a brief, dazzling flare of light that fades almost as quickly as it appeared in cosmic terms. Some starburst galaxies are so prolific in their star formation that they are producing stars faster than their gas supply can sustain, meaning the burst is temporary, a brief, incandescent flare of creativity that will exhaust itself in a few tens of millions of years. This is a cosmically short time. The starburst is a sprint, not a marathon, a sudden burst of generation triggered by the collision and destined to fade as the available gas is consumed or expelled by the violent processes the burst itself has set in motion. The most intense starburst galaxies in the universe are called ultraluminous infrared galaxies, or ULIRGs. These are almost always the result of major galactic mergers, and they emit the bulk of their energy in the far infrared because the enormous quantities of dust produced alongside the new stars absorb the visible and ultraviolet light and re-radiate it as heat. A ULIRG can be hundreds of times more luminous than the Milky Way, yet appear relatively dim in visible light because so much of its output is hidden behind curtains of warm dust. It is only when you observe them in infrared, as missions like the Spitzer Space Telescope and the James Webb Space Telescope have done, that their true brilliance becomes apparent, like pulling back a curtain to reveal a blaze of light that had been hidden from view. ARP 220, located roughly 250 million light-years from Earth in the constellation Serpens, is one of the nearest and best studied ULIRGs. It is the product of a merger between two gas-rich galaxies that is now in its final stages, with the two galactic cores separated by only about 1,200 light-years and spiraling rapidly toward final coalescence. The starburst in ARP 220 is extraordinary. Infrared observations suggest the galaxy is forming new stars at a rate of roughly 100 to 200 solar masses per year, perhaps 100 times the rate of the Milky Way. The entire central region is so heavily shrouded in dust that almost no visible light escapes. It is one of the brightest objects in the infrared sky, radiating more energy in infrared light alone than the entire Milky Way radiates at all wavelengths combined. There is something deeply moving about the fact that the most creative moments in a galaxy's life are triggered by apparent destruction. Before the collision, each galaxy was forming stars at a calm, measured pace, producing just enough new suns to replace those that were dying. The merger disrupts that equilibrium entirely. It compresses gas that had been drifting peacefully for millions of years. It forces material together that would never have met on its own. And from that disruption, from that apparent chaos, comes the most vigorous period of star formation the galaxy will ever experience. The collision does not destroy, it awakens. Among the new stars born in a starburst, some are extraordinarily massive, 50, 80, even 100 times the mass of our Sun. These stellar giants are rare under normal conditions, but the extreme densities and pressures of collision-compressed gas favor their formation. Massive stars are also among the most short-lived stars in the universe. A star 100 times the mass of the Sun will exhaust its nuclear fuel in just 2 to 3 million years, compared to the 10 billion years our more modest Sun will burn. These stars live fast and die spectacularly, ending their brief lives as supernovae, explosions so powerful that for a few weeks, a single dying star can outshine its entire host galaxy. A single supernova can briefly radiate more energy than 10 billion suns, a beacon of destruction visible across millions of light years. The supernovae produced during a starburst have consequences that ripple far beyond the death of a single star. Each supernova explosion sends a shock wave through the surrounding gas at speeds of thousands of kilometers per second, compressing the gas further and potentially triggering yet another round of star formation in a process called triggered or sequential star formation. This creates a feedback loop where new stars are born. The most massive die quickly in supernova. Their deaths compress more gas, and still more stars are born from the wreckage. The result is a cascading chain reaction of stellar birth and death that can sustain the starburst for millions of years, each generation of stars seeding the conditions for the next. Supernovae also enrich the gas with heavy elements heavier than hydrogen and helium, including carbon, oxygen, nitrogen, silicon, iron, gold, and all the other building blocks of planets and life are forged inside stars and released into space when those stars explode. A starburst, with its elevated rate of supernova explosions, floods the surrounding gas with these heavy elements far more rapidly than normal star formation would. This means that the stars formed in the later stages of a starburst are born from gas that is richer in heavy elements than the gas that formed the earlier generations. Each wave of creation leaves the raw material a little more complex, a little more chemically interesting, a little more capable of eventually producing rocky planets, liquid water, organic molecules, and perhaps, in some distant future, life. The collisions that create starbursts are, in a very real sense, the universe's way of accelerating its own chemical evolution, of building complexity from simplicity through the patient mechanics of gravity, compression, and nuclear fusion. There is a connection here to our own existence that is worth pausing over. The Sun, our star, is a third-generation star, meaning it formed from gas that had already been processed through at least 2 previous generations of stars. The heavy elements in our solar system, the iron in your blood, the calcium in your bones, the oxygen you are breathing right now, were all forged in the cores of stars that lived and died long before the Sun was born. Some of those elements may well have been produced during starburst events, triggered by ancient galactic mergers, compressed into existence by collisions that happened billions of years before Earth formed. We are, in a very literal sense, children of galactic collisions. The atoms that compose our bodies may owe their existence to the violent, creative meeting of galaxies that occurred when the universe was young. When 2 galaxies merge, it is not only the stars and gas that interact. Each galaxy carries at its center a supermassive black hole, an object so dense that not even light can escape its gravitational pull. These black holes are not small. The supermassive black hole at the center of the Milky Way, Sagittarius A star, contains roughly 4 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. If you could somehow place Sagittarius A star where the Sun is, its event horizon, the boundary beyond which nothing can escape, would extend roughly 12 million kilometers from its center, about a third of the distance from the Sun to Mercury. Everything within that boundary is lost forever, including light itself. The supermassive black hole at the center of Andromeda is estimated to be 100 to 230 million solar masses, perhaps 50 times more massive than our own Sagittarius A star. And in some galaxies, the central black holes are true monsters, containing billions of solar masses compressed into a region that, while vast in human terms, is tiny compared to the galaxy around it. The black hole at the center of the giant elliptical galaxy, Messier 87, the one famously imaged by the Event Horizon Telescope in 2019, contains roughly 6.5 billion solar masses. Its event horizon is larger than our entire solar system, and yet it sits at the center of a galaxy containing trillions of stars, a mathematical point of infinite density surrounded by a luminous city of light that extends for hundreds of thousands of light years in every direction. During a galactic merger, the two supermassive black holes begin a long, slow journey toward each other. Initially, they are separated by the same distance as the galaxies themselves, potentially millions of light years. As the galaxies approach and begin to merge, the black holes are carried along with the dense stellar cores of their respective galaxies, sinking toward the center of the combined system through a process called dynamical friction. As each black hole moves through the surrounding sea of stars, it gravitationally deflects nearby stars, flinging them away, and in the process, losing a small amount of its own kinetic energy. This drain of energy causes the black hole to slow down and spiral inward, like a ball bearing sinking through honey. But the final stages of this approach are not straightforward. Once the two black holes are within a few light years of each other, a problem arises. This problem has a name. It is called the final parsec problem, and it has puzzled astronomers for decades. The issue is this: when the two black holes are far apart, they lose orbital energy efficiently by interacting with the surrounding stars through dynamical friction. Stars that pass close to the black hole pair are flung outward at high velocities, carrying away energy and causing the black holes to spiral closer together. But as the black holes draw closer and clear out the stars around them, ejecting them to wider orbits or flinging them out of the galaxy entirely, there are fewer and fewer stars left to carry away energy. The region around the black hole pair becomes depleted of stars, creating a kind of cavity in the stellar distribution. Without stars to interact with, the black holes can become stuck in a mutual orbit at a separation of roughly 1 parsec, about 3.26 light years, unable to lose enough energy to spiral any closer. They orbit each other endlessly, so close and yet unable to merge, like two dancers frozen mid-step. Or so the theory predicted. In 2023, an international collaboration of astronomers using pulsar timing arrays announced a discovery that sent ripples through the astrophysics community. Pulsar timing arrays are networks of millisecond pulsars, rapidly spinning neutron stars that emit radio pulses with extraordinary regularity, used as natural clocks to detect gravitational waves by measuring tiny fluctuations in the arrival times of their pulses. The Nanograv collaboration in North America, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array all independently detected evidence of a gravitational wave background permeating all of space, a low-frequency hum of gravitational waves rippling through the fabric of space-time. This gravitational wave background is believed to be produced by thousands of supermassive black hole pairs throughout the observable universe, slowly spiraling toward each other and eventually merging. The detection suggests that the final parsec problem is, in fact, solved, that nature finds a way to bring the black holes together. Perhaps gas from the merger provides additional friction. Perhaps the gravitational influence of a third galaxy perturbs the orbit. Perhaps other mechanisms not yet fully understood play a role. The details are still being worked out, but the conclusion is increasingly clear. The black holes do merge. The gravitational wave background is the sound of those mergers happening everywhere, all the time, across the observable universe, a cosmic hum so deep and so slow that it took decades of precise measurements to detect. It is the sound of the universe's most patient dance reaching its conclusion, played in a register so low that only the most sensitive instruments in human history can hear it. When two supermassive black holes finally merge, the event releases more energy than almost anything else in the universe. The energy is not released as light or heat, but as gravitational waves, ripples in the fabric of space-time itself that propagate outward at the speed of light. The final moments of the merger, when the two black holes spiral together in a frenzied whirl and combine into one, can release as much energy as 100 million supernovae in a fraction of a second, radiated entirely as gravitational waves. For a brief moment, the merging black holes are the most powerful single event in the universe, converting a significant fraction of their combined mass directly into gravitational radiation. The merged black hole that results is larger than either of its parents, but not quite as massive as the sum of the two. The difference, typically around 5% of the total mass, has been radiated away as gravitational wave energy. 5% might not sound like much, but when the objects involved contain millions or billions of solar masses, 5% represents an almost inconceivable amount of energy, equivalent to the total mass energy of millions of suns, converted entirely into ripples in space-time. There is also a peculiar and dramatic phenomenon that can occur during the merger. If the merger is asymmetric, if the two black holes have significantly different masses, or are spinning in different directions, the gravitational waves they emit are not radiated equally in all directions. This asymmetry creates a recoil effect, a gravitational kick that can propel the newly merged black hole at enormous speed. In extreme cases, theoretical calculations suggest that this gravitational recoil can exceed 5,000 kilometers per second, which is fast enough to eject the merged black hole entirely from its host galaxy. The galaxy would be left without a central black hole, and the ejected black hole would sail off into intergalactic space, carrying with it a small retinue of stars gravitationally bound to its vicinity. A runaway supermassive black hole, wandering the void between galaxies, forever untethered from any home. There is some observational evidence that such events have occurred. In 2017, astronomers using the Hubble Space Telescope and the Chandra X-ray Observatory identified a candidate runaway supermassive black hole in a galaxy cluster roughly 8 billion light-years from Earth. The object appeared to have been kicked out of its host galaxy during a merger and was racing through intergalactic space, trailing a stream of shocked gas behind it, visible in X-ray emission. If confirmed, it would be a black hole with a mass of perhaps 1 billion suns, hurtling through the void at a significant fraction of the speed needed to escape its host cluster entirely, a cosmic refugee created by the violence of a merger. As gas is funneled toward the supermassive black holes during a merger, something extraordinary can happen. The gas does not simply fall straight in. Because it carries angular momentum, it forms a rapidly rotating disk around the black hole, called an accretion disk, where friction between adjacent layers of gas converts orbital energy into heat, warming the material to temperatures of millions of degrees. This superheated gas radiates enormous amounts of energy across the electromagnetic spectrum, from radio waves through infrared, visible light, ultraviolet, X-rays, and even gamma rays. When this process is active, the region around the black hole becomes what astronomers call an active galactic nucleus, or AGN. In its most luminous form, an AGN can outshine the entire galaxy that hosts it by factors of 10, 100, or even 1,000, becoming a quasar, one of the most luminous sustained phenomena in the universe. A single quasar can radiate more energy than 1 trillion suns. The most luminous quasars known, are visible at distances of more than 13 billion light years, their light having traveled for nearly the entire age of the universe. They are powered by supermassive black holes, consuming gas at prodigious rates, sometimes swallowing the equivalent of several Earth masses per second. The energy released by this accretion process is extraordinarily efficient, converting roughly 10% of the accreted mass into radiation, compared to the roughly 0.7% efficiency of nuclear fusion in stars. Pound for pound, a quasar is more than 10 times more efficient at producing energy than a star. Quasars are overwhelmingly found in its early universe at high redshifts, during a time when galactic mergers were far more frequent than they are today. This is not a coincidence. The connection between mergers and quasar activity has been studied extensively, and while not every merger produces a quasar, the most luminous quasars are almost always associated with galaxies that are interacting or have recently merged. The collision funnels vast quantities of gas toward the center of the galaxy, feeding the supermassive black hole and igniting the AGN. In a sense, the quasar is the black hole's response to being fed by a collision. It is the most energetic protest against having too much matter delivered too quickly. Active galactic nuclei do not just radiate light. They also drive powerful outflows of gas away from the galaxy in the form of relativistic jets, narrow beams of plasma accelerated to speeds approaching that of light, and broad winds that can extend hundreds of thousands of light years into intergalactic space. These outflows carry enormous amounts of energy and momentum, and they can have a profound effect on the galaxy's ability to form stars. By heating or expelling the cold gas that would otherwise collapse into new stars, AGN feedback can actually shut down star formation in a galaxy, bringing the starburst to an end and transforming the galaxy from a vigorous star-forming system into a quiet, passive one. This is one of the great ironies of galactic mergers. The collision triggers a burst of star formation, but the very same collision also feeds the central black hole, which eventually grows powerful enough to blow away the remaining gas and shut down the star formation it helped to create. The black hole acts as both the beneficiary and the executioner of the merger's creative burst. It grows fat on the gas delivered by the collision, and then uses the energy of its own feeding to destroy the conditions that were feeding it. It is a self-regulating system, a cosmic thermostat that prevents galaxies from forming too many stars, and it explains one of the most puzzling observations in extragalactic astronomy: the fact that the most massive galaxies in the universe are also the deadest, the ones with the least ongoing star formation, despite having the largest reservoirs of potential fuel. Galactic mergers do not happen in isolation. They happen within the larger framework of cosmic structure, the vast web of matter that spans the observable universe. This framework is called the cosmic web, and it consists of long filaments of dark matter and gas connecting dense nodes where galaxy clusters reside, with enormous voids of nearly empty space in between. If you could somehow see the entire observable universe from a great distance, it would look remarkably like a biological structure, a vast three-dimensional network of connected threads and junctions, like the neural network of a brain or the mycelium of a fungus, stretching across billions of light years. Galaxies are not scattered randomly through this web. They are threaded along its filaments like beads on a string, and the places where filaments intersect are where the largest concentrations of galaxies are found. Galaxy clusters, the largest gravitationally bound structures in the universe, sit at the nodes of the cosmic web, containing hundreds or thousands of galaxies packed into a relatively small volume of space, typically a few million light years across. Within these clusters, galactic mergers are common. Galaxies pass close to each other frequently, their gravitational fields overlapping and interacting, producing tidal distortions, starbursts, and full mergers. The Virgo cluster, the nearest large galaxy cluster to our own local group, contains more than 1,300 galaxies spread across roughly 15 million light-years of space. At its center sits the giant elliptical galaxy Messier 87, or M87, one of the most massive galaxies known. S87 is almost certainly the product of many galactic mergers over billions of years. Its smooth, featureless elliptical shape, its enormous population of roughly 15,000 globular star clusters, an order of magnitude more than the Milky Way's roughly 150, its lack of spiral structure, and its monstrous supermassive black hole, all point to a long history of consuming smaller galaxies and growing through merger after merger. M87 is the apex predator of the Virgo cluster, a galaxy that has been eating its neighbors for billions of years. In the dense cores of galaxy clusters, a particular kind of galactic interaction occurs that is less dramatic than a full merger, but no less consequential. It is called galaxy harassment, and it describes the cumulative effect of repeated high-speed encounters between galaxies in a cluster environment. In a galaxy cluster, galaxies move at velocities of hundreds or even thousands of kilometers per second relative to each other, much faster than the velocities typical of galaxy pairs in the field. At these speeds, galaxies do not have time to merge. They pass by each other too quickly for gravity to bind them together. But each close passage delivers a gravitational impulse that disturbs the galaxy's structure, heating its stellar disk, stripping away some of its outer gas, and gradually transforming its morphology over cosmic time. Over billions of years and dozens of such encounters, a small spiral galaxy in a cluster can be transformed into a smooth, featureless dwarf elliptical, its spiral arms erased not by a single dramatic collision, but by the accumulated effects of many brief, high-speed interactions. It is not a single blow that reshapes the galaxy. It is 1,000 small nudges delivered over cosmic time, each one individually insignificant, but collectively transformative. Galaxy harassment is one of the reasons why galaxy clusters are dominated by elliptical and lenticular galaxies rather than spirals. The cluster environment gradually grinds the spirals down, smoothing their structures through repeated gravitational encounters. There is another process that occurs specifically in galaxy clusters, and it is one of the quietest and most poignant forms of galactic transformation. It is called RAM pressure stripping, and it happens when a galaxy moves through the hot, thin gas that fills the space between galaxies in a cluster. This gas, called the intracluster medium, is extraordinarily hot, tens of millions of degrees, heated by the gravitational energy released as the cluster assembled and by shock waves from merger events. Despite its extreme temperature, the intracluster medium is incredibly sparse by terrestrial standards, just a few particles per cubic centimeter, a better vacuum than anything achievable in a laboratory on Earth. But at the velocities galaxies move through it, sometimes exceeding 1,000 kilometers per second, the drag effect is substantial. As a galaxy plunges through the intracluster medium, the gas within the galaxy is pushed backward by the pressure of the surrounding hot medium, like smoke trailing behind a car on a highway, or like the hair of a swimmer streaming backward as they dive underwater. Over millions of years, this ram pressure can strip away most or all of a galaxy's cold gas supply, removing the raw material it needs to form new stars. Galaxies that have been stripped of their gas in this way are sometimes called quenched galaxies because their star formation has been extinguished. They continue to exist as collections of aging stars, growing gradually redder and dimmer as their existing stars burn through their fuel and no new ones are born to replace them. These quenched galaxies are common in the centers of clusters, where the intracluster medium is densest and the ram pressure is strongest. The Hubble Space Telescope has captured images of ram pressure stripping in action that are both beautiful and melancholy. In the Coma Cluster, roughly 320 million light-years from Earth, several galaxies have been photographed with long tails of stripped gas trailing behind them, glowing in ultraviolet and hydrogen alpha emission. These tails can extend hundreds of thousands of light-years behind the galaxy, and in some cases they contain star-forming regions, small knots of compressed gas within the stripped material that have begun to collapse and form stars outside the galaxy that produce them. Stars born in the wake of a stripped galaxy, drifting through the void between cluster members belonging to no galaxy at all. Orphan stars, created from stolen gas, glowing quietly in the space between worlds. One of the most spectacular examples of RAM pressure stripping in the nearby universe is the galaxy known as ESO 137-001, located in the Norma cluster roughly 220 million light-years from Earth. This spiral galaxy is plunging through the center of its cluster at high speed, and the RAM pressure has pulled an enormous tail of hot gas behind it, visible in X-ray observations from the Chandra X-ray Observatory. The tail extends more than 250,000 light-years behind the galaxy, longer than the diameter of the Milky Way, and contains both hot, X-ray emitting gas and cooler clumps of hydrogen that are forming new stars. ESO 137-001 is a galaxy being slowly undressed by its environment, its gas peeled away layer by layer as it moves through the cluster, leaving a trail of stellar debris in its wake like a comet's tail stretching across intergalactic space. Every major galactic merger follows a broadly similar sequence, though the details depend on the masses of the galaxies involved, their relative velocities, the angle of approach, the gas content of each galaxy, and the orientations of their disks relative to their orbital plane. The sequence unfolds over roughly 1 to 3 billion years, from first interaction to final coalescence, and it can be divided into several distinct phases. The first phase is the approach. The two galaxies fall toward each other under gravity, their dark matter halos beginning to overlap long before the visible disks come close. Tidal forces begin to distort the outer regions of each galaxy, pulling faint wisps of gas and stars from their outermost edges. This phase can last hundreds of millions of years, and during most of it, the galaxies show little visible sign of interaction. The second phase is the first passage. The two galaxies pass through or close to each other for the first time. If the approach is close enough, the tidal interaction is dramatic, pulling long tidal tails from each galaxy and compressing gas clouds in the overlapping region. A burst of star formation may be triggered, particularly in the region between the two galaxy cores, where gas compression is strongest. But the galaxies do not merge on the first pass. They continue past each other, carried by their momentum, and separate again, though now connected by bridges of stripped material and gravitationally bound to return. After the first passage, the two galaxies may be separated by hundreds of thousands of light years, slowly decelerating, reaching the apex of their separation, and then beginning the long fall back toward each other. The third phase is the return. Having passed each other, the two galaxies slow, stop, and begin to fall back toward each other again. This return approach is often faster than the first because the galaxies are now closer together and more tightly gravitationally bound. The tidal distortions continue to grow, the gas compression intensifies, and the starburst activity may increase as the second encounter approaches. The fourth phase is the final coalescence. The two galaxies pass through each other again, and this time the interaction is so close and so disruptive that they do not separate. Their stellar cores merge. Their gas pools into a combined structure, and the combined system begins to settle into a new equilibrium. The starburst reaches its peak during this phase, and the supermassive black holes at the centers of the two galaxies, begin their own slow spiral toward merger, sinking to the center of the combined system through dynamical friction. The fifth and final phase is the relaxation. Over hundreds of millions to a billion years after coalescence, the merged system gradually settles into its final form. The tidal tails slowly fall back into the galaxy or dissipate into intergalactic space. The starburst fades as the available gas is consumed or expelled by supernova winds and AGN feedback. The stellar orbits, initially chaotic and disordered from the violence of the merger, gradually randomized through gravitational interactions into the smooth, isotropic velocity distribution characteristic of an elliptical galaxy. The supermassive black holes complete their merger, sending a final burst of gravitational waves rippling through the cosmos. And eventually, the system reaches a new equilibrium, a single, larger, calmer galaxy where once there were two. Modern computer simulations have been essential to our understanding of this entire sequence. The process is far too slow to observe in real time. No human civilization could watch a merger unfold from start to finish, so astronomers must rely on two complementary approaches. First, they observe many different mergers at different stages, assembling the full sequence from snapshots, like studying a forest by photographing individual trees at different ages. Second, they build computer simulations that model the gravitational interactions of billions of particles over billions of years, creating virtual mergers that can be played forward from beginning to end in a matter of hours or days of computing time. Since the Tumri brothers' pioneering work in 1972, simulations have grown enormously in scale and sophistication. Modern merger simulations, like those produced by the illustrious TNG project, the Fire Collaboration, and the Eagle project, model not just gravity but also gas dynamics, radiative cooling, star formation, supernova feedback, black hole accretion, AGN feedback, magnetic fields, and cosmic ray physics, using billions of resolution elements tracked across billions of years of simulated time. These simulations run on some of the largest supercomputers in the world and can take months to complete even a single merger scenario, but the results are extraordinary. They produce virtual merging galaxies that match the observed shapes, star formation rates, gas distributions, chemical enrichment patterns, and black hole properties of real systems with remarkable fidelity. One of the most important insights from simulations is that the outcome of a merger depends sensitively on the initial conditions. The angle of approach matters enormously. A head-on collision produces a very different result from a glancing encounter. The relative spin orientations of the two galaxy disks matter, whether they are spinning in the same direction as their mutual orbit, producing prograde encounters, or in opposite directions, producing retrograde encounters. Prograde encounters tend to produce longer, more dramatic tidal tails, because the orbital motion and the disk rotation reinforce each other on the side of the galaxy facing the companion. Retrograde encounters produce shorter, stubbier tails. The gas fractions matter, with gas-rich mergers producing more dramatic starbursts and more luminous AGN. The mass ratio matters, with equal mass mergers producing the most dramatic transformations and minor mergers producing subtler effects. This sensitivity to initial conditions means that no two galactic mergers are exactly alike. Each one is a unique event, shaped by the particular circumstances of that specific encounter. The antennae galaxies look different from the mice galaxies, which look different from the cartwheel galaxy, which looks different from the whirlpool galaxy, and each of those differences can be traced back to the specific geometry, velocity, mass ratio, and gas content of the initial interaction. The universe does not repeat itself when it merges galaxies. Every collision is a new creation, a one-of-a-kind sculpture carved by gravity from the raw material of two unique galaxies meeting under unique conditions. Our own galaxy has not been immune to collisions. The Milky Way has a long history of consuming smaller galaxies, and the evidence of those past mergers is written into the structure, chemistry, and motions of our galaxy's stars. In 2018, a team of astronomers using data from ESA's Gaia Space Observatory, which is mapping the positions, distances, and motions of nearly 2 billion stars in the Milky Way with unprecedented precision, discovered evidence of a major ancient merger that fundamentally shaped the galaxy we inhabit today. Roughly 8 to 11 billion years ago, the young Milky Way collided with a substantial galaxy that has been named Gaia Enceladus, or the Gaia Sausage, after the distinctive, elongated, sausage-shaped distribution of its star's orbits in velocity space. Gaia Enceladus was not a small galaxy. It is estimated to have been roughly a quarter to a third the mass of the Milky Way at the time, making this a significant merger by any standard. Its absorption contributed a large fraction of the stars in our galaxy's inner stellar halo and thick disk. The puffier, more vertically extended population of older stars that surrounds the thin disk where the sun resides. Many of the stars you see in the night sky, stars that appear to be ordinary members of the Milky Way, are actually immigrants, captured from a galaxy that no longer exists independently. They orbit our galactic center on paths that still carry the gravitational memory of their former home. Their orbits more elongated and more inclined than those of stars born in the Milky Way's disk, a kinematic signature of their extragalactic origin that persists billions of years after the merger was complete. The Gaia-Enceladus merger was not the only one. The Milky Way has consumed numerous smaller galaxies over its lifetime, and the debris of those ancient meals is scattered throughout the galaxy. The Sagittarius Dwarf elliptical galaxy, located on the far side of the Milky Way's center, roughly 70,000 light-years from Earth, is currently being torn apart by our galaxy's tidal forces. It has been orbiting the Milky Way for at least 2 billion years, making several complete orbits, and on each passage around the galaxy, it loses more of its stars to tidal stripping. Its stars are being stretched into long streams that wrap around the Milky Way like ribbons around a maypole. These streams, called the Sagittarius Stream, have been mapped across the entire sky using data from multiple surveys and contain hundreds of millions of stars that once belonged to the Sagittarius Dwarf, but are now being absorbed into the Milky Way's halo. The Magellanic Clouds, the two small, irregular galaxies visible from the southern hemisphere, are also interacting with the Milky Way, though their fate is less certain. For decades, astronomers believed the large and small Magellanic Clouds were long-term satellites of the Milky Way that had been orbiting our galaxy for billions of years. But recent measurements of their velocities using data from the Hubble Space Telescope and ESA's Gaia mission suggest that the Magellanic Clouds may be on their first approach, falling toward the Milky Way for the first time and not yet gravitationally captured into a stable orbit. If this is correct, then the Magellanic Clouds are in the earliest possible stage of a galactic interaction, the first tentative approach before the long gravitational drama begins. Trailing behind the Magellanic Clouds is a vast stream of hydrogen gas called the Magellanic Stream, stretching more than 200 degrees across the sky, nearly halfway around the entire celestial sphere. This stream contains enough gas to form roughly 2 billion new stars and was pulled from the Magellanic Clouds by the tidal forces of the Milky Way and by interactions between the two clouds themselves. It is a tidal tail in formation, a signature of interaction that mirrors on a smaller scale the great tidal tails seen in the antennae and mice galaxies millions of light-years away. The same physics, the same patient gravitational sculpting, happening right here in our own cosmic backyard, and then there is the collision that lies in our future. The event that has been building for billions of years, and will reshape our corner of the universe more dramatically than anything that has happened since the Milky Way was young. The merger of the Milky Way and Andromeda. The timeline of this merger has been refined significantly in recent years. Current estimates place the first close passage approximately 4.5 billion years from now, though some models suggest it could occur as early as 3.9 billion years or as late as 5.5 billion years. The uncertainty arises primarily from imprecise knowledge of Andromeda's transverse velocity, its sideways motion across the sky, which is extremely difficult to measure at such an enormous distance. Hubble Space Telescope observations published in 2012 by a team led by Roland van der Merel provided the first reliable measurement of this transverse velocity, confirming that the collision is nearly head-on, not a glancing blow, which means the merger will be thorough and complete. The merger will not happen all at once. After the first close passage, the two galaxies will separate again, their cores retreating from each other while connected by bridges and tails of stripped material, much as the mice galaxies are connected today. This separation may last another billion years or so before gravity draws them back for a second, closer encounter. This second passage will be more disruptive than the first, and the two galaxies are unlikely to separate again. Over the following 1 to 2 billion years, the merged system will gradually settle into a single, larger galaxy. Astronomers have given this future galaxy a name. It is called Milkomeda, a blend of Milky Way and Andromeda, though some prefer the alternative name Milkdromeda. What will the merger look like from Earth, assuming Earth still exists? Remarkably, the Sun is expected to survive the event. In 4.5 billion years, our Sun will be nearing the end of its main sequence lifetime, approaching the red giant phase but not yet there. The solar system will still exist, and Earth, though it may be considerably warmer and less hospitable than today, will still be orbiting. The merger itself will pose no direct threat to our solar system. The distances between stars are simply too vast for the merger to bring any foreign star close enough to our Sun to disrupt planetary orbits. The probability of another star passing within 1 light year of the Sun during the entire merger is extremely low. The Sun and its planets will drift through the merger as peacefully as a boat on a gentle current, the surrounding galaxy reshaping itself around us while our little corner of space remains essentially undisturbed. But the sky will change. The view will be extraordinary. Today, Andromeda is a faint smudge, visible only under dark skies. But as it approaches over the next few billion years, it will grow larger and larger, its spiral form stretching across an ever greater arc of the sky. By the time the first passage is imminent, Andromeda will span a significant portion of the heavens, its spiral arms clearly visible to the naked eye, a vast pinwheel of light dominating the night sky in a way no celestial object does today. During the first close passage, the sky will be filled with the distorted shapes of two interacting galaxies, tidal tails sweeping across the darkness, new star-forming regions blazing with blue light, and the combined glow of more than 1 trillion stars filling the sky with a soft, diffuse luminance unlike anything we see today. Night will be brighter. The darkness between stars will be less absolute. The familiar constellations will be rearranged as the gravitational upheaval shifts. Stellar positions, slowly, over millions of years, but inexorably. And eventually, once the merger is complete and the combined system has settled into its final elliptical form, the band of the Milky Way, that familiar river of light that has graced human skies since the first eyes looked upward, will be gone. In its place will be a smooth, even glow of stars in every direction, the signature of an elliptical galaxy, a galaxy without the distinct arms, without the dark lanes of interstellar dust, without the structured beauty of a spiral, something will have been lost, and something new will have been born. The Milky Way Andromeda merger will not be the final chapter either. The Triangulum Galaxy, also known as Messier 33, the third largest member of our local group, is expected to be drawn into the merger as well, either during the initial Milky Way Andromeda interaction or shortly afterward. Triangulum is a small, gas-rich spiral galaxy roughly 2.7 million light-years from Earth, and its relatively low mass means it will likely be absorbed without significantly altering the outcome of the main merger. It will add its gas, its stars, and its dark matter to the growing combined system, one more ingredient in the cosmic recipe that produces Milkomeda. And over much longer timescales, the other galaxies of the local group, the dozens of dwarf galaxies that orbit the Milky Way and Andromeda, will gradually fall inward and be absorbed. Eventually, over tens of billions of years, the entire local group will merge into a single enormous elliptical galaxy. Every galaxy that is currently gravitationally bound to us will become part of one unified structure. Beyond the local group, something very different will be happening. While our local galaxies merge together, the galaxies beyond our gravitational reach will be receding from us, carried away by the accelerating expansion of the universe, driven by dark energy. The expansion is not slowing down, it is speeding up. Every year, the distant galaxies move a little faster away from us, and the volume of observable universe grows a little smaller in terms of what we can communicate with or ever reach. Galaxies that are currently visible in our telescopes will gradually redshift beyond detection, their light stretched to wavelengths too long for any instrument to capture. The cosmic horizon, the boundary beyond which light can never reach us no matter how long we wait, will draw closer and closer. In the very far future, perhaps 100 billion years from now, the only galaxy visible in the sky will be our own merged remnant, Milkomeda. Every other galaxy in the observable universe will have passed beyond the cosmic horizon, their light red-shifted into silence. The night sky will contain the ancient stars of our merged galaxy and nothing else. No distant galaxies twinkling in deep exposures, no quasars blazing at the edge of the universe, no filaments of the cosmic web faintly visible in survey images. Just one galaxy, alone in an expanding void, with no visible evidence that the rest of the universe ever existed. There is something profound about this vision of the far future. It means that the age we live in now, this particular moment in cosmic history, is special. We exist at a time when the universe is still young enough for galaxies to be visible across billions of light years, when the cosmic web is still detectable, when the cosmic microwave background still carries information about the birth of the universe. Civilizations that arise in the deep future, trillions of years from now, will have no way of knowing any of this. They will see only their one local galaxy, isolated in an empty sky, and they will have no evidence that the universe was ever any different. The cosmic microwave background will have red-shifted beyond detection. The distant galaxies will be gone. The evidence of the Big Bang itself will be erased. The history of the cosmos will be invisible to them, hidden by the very expansion that drives the universe forward. We are lucky, in a way that is almost impossible to appreciate, to be here now, when the universe still remembers its own past, when the evidence is still visible, when the story can still be read. Let us explore a few more remarkable collision stories before we begin to wind our way toward the close of tonight's journey. The Whirlpool Galaxy, Messier 51, is one of the most beautiful spiral galaxies in the sky. Located roughly 23 million light-years from Earth in the constellation Canes Venatici. Its spiral arms are extraordinarily well-defined, sweeping outward from the bright core in two graceful, continuous curves outlined by dark lanes of dust and punctuated by bright pink regions of active star formation. What makes M51 particularly fascinating is its smaller companion, NGC 5195, which sits at the end of one of M51's spiral arms, visibly connected by a bridge of stars and gas. NGC 5195 is currently passing behind and through the outer regions of M51, and the gravitational interaction between the two galaxies is what gives M51 its remarkably clean spiral structure. The companion's gravity compresses the gas in M51's disk and enhances the density waves that define the spiral arms. Without the interaction, M51's arms would likely be less pronounced, less regular, less beautiful. Sometimes a collision does not destroy structure, it sharpens it. The Whirlpool galaxy whirls because it is being gently played by the gravity of its companion, like a hand adjusting the strings of an instrument to produce a clearer note. Centaurus A, or NGC 5128, located roughly 12 million light-years from Earth, is one of the strangest galaxies visible from the southern hemisphere. It appears as a large elliptical galaxy bisected by a thick, dark band of dust that cuts across its middle like a belt. This dust lane is the remnant of a spiral galaxy that was consumed in a merger perhaps a few 100 million years ago. The smaller spiral fell into the larger elliptical, and its disk of gas and dust has not yet been fully absorbed or dispersed. It is a fossil of the collision, a visible scar still wrapped around the body of the galaxy that consumed it. Centaurus A also hosts one of the nearest active galactic nuclei, powered by a supermassive black hole estimated at 55 million solar masses, with two enormous jets of relativistic plasma extending more than 1 million light-years in opposite directions. These jets are fueled by gas delivered to the galaxy's center during the merger. Centaurus A is a galaxy still digesting its last meal. Stephan's quintet, discovered by astronomer Edward Stephan in 1877, is one of the most studied compact galaxy groups in the sky. Located roughly 290 million light-years from Earth in the constellation Pegasus, it consists of 5 galaxies crowded into a region of space only about 300,000 light-years across. 4 of the 5 galaxies are physically associated and actively interacting, their gravitational fields producing a complex web of tidal tails, gas bridges, and shock-heated gas. One of the group's galaxies, NGC 7318b, plunged into the group at roughly 870 kilometers per second, creating a shock wave larger than the Milky Way visible in X-ray and radio observations. This shock was one of the first targets imaged by JWST, which revealed extraordinary detail in the heated gas and triggered star formation. Over the next few billion years, the 4 interacting galaxies are expected to merge into a single elliptical galaxy. There is a galaxy that tells one of the most unusual collision stories in all of astronomy. NGC 1052-DF2 is an ultra-diffuse galaxy, roughly 65 million light-years from Earth, that appears to contain almost no dark matter. Its stars move at velocities consistent with the gravity of the visible matter alone. This is profoundly unusual, since nearly every galaxy ever observed is dominated by dark matter. One leading explanation is that NGC 1052-DF2 was created during a high-speed collision between 2 galaxies. When galaxies collide at extreme velocities, the dark matter, which interacts only through gravity, passes through undisturbed. But the ordinary gas collides, is separated from the dark matter, and can collapse to form a new galaxy that contains almost no dark matter at all. NGC 1052-DF2 may be the orphaned remnant of such an event, a galaxy that should not exist, proof of how galactic collisions can produce structures that violate our most basic assumptions about how galaxies are built. Galaxy cluster mergers represent the most extreme end of the collision spectrum. Events so energetic, they dwarf even the most violent individual galaxy mergers. When two galaxy clusters collide, the event involves not just hundreds or thousands of galaxies, but also the vast reservoirs of hot gas, the intracluster medium that fill the space between the galaxies in each cluster. The total mass involved can exceed 1,000 trillion solar masses, and the energy released can exceed 10 to the power of 64 joules, more than 1 trillion supernovae detonating simultaneously. The Bullet Cluster, located roughly 3.7 billion light-years from Earth, provides the most famous example. In this system, two galaxy clusters pass through each other at roughly 4,500 kilometers per second. The hot gas from each cluster collided and slowed down, piling up in the center of the system. But the dark matter in each cluster, which does not interact except through gravity, passed straight through, continuing on its original trajectory. Gravitational lensing observations, which map the distribution of mass by measuring how it bends the light of background galaxies, show that the bulk of the mass is located ahead of the hot gas, in regions where the dark matter has sailed through. The Bullet Cluster is one of the strongest pieces of direct evidence for the existence of dark matter as a distinct substance, separate from ordinary matter, because it shows the two being physically separated by a collision. The Able II 744 cluster, sometimes called Pandora's cluster, is one of the most complex merging systems ever observed. Located roughly 3.5 billion light-years from Earth, it appears to be the result of at least 4 separate galaxy clusters colliding simultaneously, producing a tangled web of shock-heated gas, stripped galaxies, and separated dark matter concentrations. Pandora's cluster was chosen as one of JWST's first deep field targets, and the resulting images revealed thousands of extremely distant background galaxies, their light bent and magnified by the cluster's enormous gravitational field. Even in its violence, a cluster collision creates a natural telescope, bending space-time in ways that reveal more of the universe to our eyes. The story of galactic mergers is also a story about how the universe's character has changed over time. In the early universe, when the cosmos was only a few billion years old, mergers were far more frequent. Galaxies were smaller, closer together, and still assembling themselves from the bottom up, growing through repeated collisions. The universe at that time was a crowded, chaotic, creative place. The Hubble Ultra Deep Field, a tiny patch of sky that Hubble stared at for more than 11 days, contains roughly 10,000 galaxies in an area smaller than a grain of sand held at arm's length. Many of those galaxies, seen as they were 10 or 11 billion years ago, are clearly irregular, distorted, or interacting. Mergers were everywhere. The early universe was a construction site, and collisions were the primary building tool. The James Webb Space Telescope has pushed this view even further. JWST has detected galaxies merging when the universe was less than 1 billion years old, confirming that collisions began almost as soon as galaxies themselves existed. But as the universe has expanded and aged, the merger rate has declined. Galaxies today are further apart, and the expansion of space carries most galaxy pairs away from each other faster than gravity can draw them together. The era of frequent collisions is drawing to a close, and we happen to live near its end. Astronomers classify mergers by mass ratio and gas content. A major merger involves galaxies of similar mass. A minor merger involves a much smaller galaxy being absorbed by a larger one. Wet mergers involve gas-rich galaxies and produce dramatic starbursts. Dry mergers involve gas-poor ellipticals and can proceed almost silently, with no new star formation at all. Just a quiet gravitational reshuffling of ancient stars. Mixed mergers produce hybrid outcomes. Each type leaves different signatures in the merged galaxy's structure, chemistry, and stellar populations, allowing astronomers to read the merger history of a galaxy from its present-day properties, like reading the rings of a tree to learn about the seasons it has lived through. And now, as we near the end of tonight's exploration, let us take a moment to think about what all of this means together. We have journeyed from the smallest gravitational whisper between two distant galaxies to the most energetic events in the cosmos. From the patient approach of the Milky Way and Andromeda to the searing violence of galaxy cluster mergers, from the gentle extraction of tidal tails to the nuclear fury of starbursts, from the silent drift of dark matter halos to the deepest hum of gravitational waves. And through all of it, one theme has repeated itself, quietly, persistently, like a bass note beneath a symphony. Patience. Gravity is patient. Time is patient. The universe is patient. Everything that seems dramatic and sudden in cosmic terms is, in fact, the product of unimaginably long processes unfolding at their own unhurried pace. A galactic merger that takes 2 billion years from first approach to final coalescence is not an event. It is an era. It is a chapter of cosmic history longer than the entire age of complex life on Earth. And yet, from a sufficient distance, it looks like a single frame in a slideshow, a frozen moment captured by a telescope and rendered as an image that fits on a screen. There is something humbling about that, something that puts our own sense of time into perspective. We worry about tomorrow. We plan for next year. We dimly imagine next decade. But the universe operates on time scales where 1 billion years is a reasonable unit of measurement, where the word soon can mean in a few 100 million years, where patience is not a virtue, but a fundamental property of reality. The collision between the Milky Way and Andromeda will begin in roughly 4.5 billion years. If you could leave a note for the beings alive at that time, the note would have to survive longer than the entire current age of multicellular life on Earth. That is the scale of the universe's patience. That is the clock by which gravity keeps time. And yet here we are, tiny and brief and warm, lying in the dark and thinking about it all. There is something extraordinary about that beings who live for decades can comprehend processes that span billions of years, that minds which evolved to track the movement of predators across a savanna can grasp the gravitational interaction of structures containing 1 trillion stars. We are small, but we are not simple. And the fact that we can wonder about these things, that we can feel awe at the scale and patience of the cosmos, is itself a product of billions of years of stellar evolution, planetary chemistry, and biological complexity, much of it shaped by the very galactic collisions we have been exploring tonight. Galaxy collisions are stories about patience. They are stories about the longest timescales the universe has to offer, the slowest and most deliberate processes in nature. They remind us that change does not have to be sudden to be profound, that destruction and creation are not opposites, but partners, that the most beautiful things in the cosmos are often born from apparent chaos, and that gravity, the weakest force in the universe, can reshape everything, given enough time. So if you are still awake, let that thought settle gently into the quiet of your mind. The universe is patient. It does not rush. It does not hurry. It takes its time, and in that time, it creates wonders beyond anything we could imagine. You are part of that patience. You are made of atoms that were forged in stars, that were born in collisions billions of years ago. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all of it was created in stellar furnaces that may have been ignited by the compression of galactic mergers. You are, in a very real sense, a child of these ancient, patient, beautiful events. And if your eyes are growing heavy, that is perfectly fine. Let them close. Let the images of colliding galaxies drift through your mind like light through dust, soft and warm and slowly fading. The universe will still be here when you wake. The galaxies will still be dancing, the stars will still be forming, and gravity will still be reaching across the void, patient as always, connecting everything to everything else with the gentlest touch in nature. Somewhere out there, right now, two galaxies are meeting for the first time. Their dark matter halos are touching. Their outermost stars are beginning to feel the tidal pull. Somewhere, tidal tails are forming, great arcs of starlight being drawn across the void. Somewhere, gas clouds are colliding at hundreds of kilometers per second, compressing, fragmenting, and igniting into millions of new stars. Somewhere, two supermassive black holes are spiraling toward each other, their gravitational waves rippling through space-time like the lowest note of a cosmic symphony too deep for any ear to hear. And somewhere, in a galaxy not so different from our own, a quiet star is shining on a small world where someone might be looking up at a sky being slowly reshaped by a collision that began before their world existed. They might see the same tidal tails, the same starbursts, the same slow and graceful dance, and they might feel the same quiet wonder that you are feeling now. The universe is dancing. It has always been dancing, and the dance will go on long after you and I are part of the stardust it is made from. Sleep well, and I will see you next time.